Section 6-2 is on the antiderivative of the reciprocal function and another form of FTC. That's the fundamental theorem of calculus. The objective of this section is to find out how to differentiate a function defined as a definite integral with a variable as the upper limit. So we're talking about a definite integral, the definite integral from a to b of some function, where the b part of that is some variable. So let's take a look at an example, at least to start off with here. Here's an example of a function defined as a definite integral. F of x is equal to the definite integral from 1 to x of sine of t dt. And it says to find f prime of x. So the first thing we need to do is find out if we can write f of x just as a function without the definite integral notation. So that's what we're going to start out with. So we'll say f of x is equal to the antiderivative of sine of t is equal to a negative cosine of t. And we evaluate that from 1 to x, just using our first form of fundamental theorem that we know. Find the antiderivative and then evaluate at the upper bound and the lower bound and take the difference. So let's now evaluate at the upper bound. So it's a negative cosine of x. That's the upper bound. And then minus the lower bound is going to be a negative cosine of 1. So this turns out to be equal to negative cosine of x and then plus cosine of 1. I'm not sure exactly what cosine of 1 is equal to, but it's some constant, of course. You could punch that in your calculator and see what value you get. All right, so there's what f of x is equal to, but the question wasn't to find f of x. It was to find the derivative of f of x, to find f prime of x. So got one more step here. So f prime of x, given our function that we just came up with, just take the derivative of it. Derivative of a negative cosine of x is going to be a positive sine of x. And the derivative of cosine of 1, again, we said that's just some constant. And of course, the derivative of a constant is 0. And so we end up with just the sine of x. So notice that we end up with the same function that we started with. We started out with sine of some value t. And we ended up with sine of x here at the end. The only difference is that we ended up with this as the sine of x instead of the sine of t. So in other words, it looks like we've in essence taken the upper bound and done a substitution here in order to get this final result. So in other words, it looks like I could speed up this process a little bit. I don't need to go through the process of first finding the antiderivative, so I can then later find the derivative of that. I can speed it up by making a note of this little property here. And so that's actually the second form of the fundamental theorem of calculus. So there's two ways we'll write this down. Sometimes this is referred to the second form of the fundamental theorem of calculus. Our book refers to it as the derivative of an integral form. But and I might refer to both of those as we go through this chapter, but those mean the same thing here. Here's how the book puts it, and we're going to write it a second way, like I said. The first way that the book says it is this: if g of x is equal to the integral from a to x, a is a constant and x is our upper bound, just like our example we just had, of f of t dt, where a is some constant, and secondly, if f is continuous close to a, so we just have to have a function that's continuous around a, near a. And if that's the case, then it turns out that g prime of x is just equal to f of x, not f of t, not f of t like we have here, but rather it's f of x, which is what we noted there, that looks like we just take that upper bound and we substituted it in, and we ended up with what our derivative was. And that's the property we just looked at in that example. All right, the second way that you can write this is sometimes the upper bound, in fact I should say many times, you'll find that the upper bound is not just x, but rather it's some function of x. So we've changed the upper bound here from just x to now h of x. So let's see how that changes this. So we say if g of x is equal to the integral from a to h of x of f of t dt. So h of x could be 2x or x squared plus 1 or sine of x or whatever. It's some function of x up there. Where a is a constant. The second condition is that f has to be continuous still close to a. And now the conclusion looks a little bit different because of the fact that that upper bound is a little different. You can still see, though, in our conclusion we're substituting in, it says g prime of x is equal to f of h of x. So it still looks like that this end result here involves this f of h of x, and it looks like what we've done is we've taken this upper bound h of x right here, and we've basically substituted into our function and replaced the t there to get f of h of x. But that's not all. There's one more part to this. It also turns out that you have to multiply by the derivative of that upper bound. So it turns out we have to multiply by h prime of x. Now, in the previous way we wrote that, of course, if the upper bound is x, the derivative of x is 1. So in essence, we kind of did do that, but multiplying by 1, of course, doesn't change the problem. So there is the second form, and that second form I would suggest is probably the one that's more important, more critical for you to know, because more often than not, you're going to find that upper bound is going to involve some function of x rather than just simply x. All right, let's take a look at the proof of this second form of this. Let me just give myself a little room here to work. So again, we're going to take this little theorem here, the second form of the fundamental theorem of calculus, the derivative of an integral form. And let's go through and see if we can prove why this is true. We saw in that last example that it looks like that's the case. Let's see if we can actually prove this thing. So let's start out by doing this. Let's let g of x be what the theorem says it's equal to. G of x is equal to the definite integral from a to h of x of f of t dt. Okay. And the second function I want to define here is what the antiderivative of f of x is equal to. So we're going to also say and k of x is equal to the antiderivative of f of x dx. And it'll just make it a little bit easier if I define that function that's the antiderivative of function f. All right, so with that, we can say this, just using our first form of the fundamental theorem of calculus, the original form that we've learned. If I want to find out what this antiderivative, or I should say this definite integral is equal to, I find the antiderivative of my function, which we've said that the antiderivative of our function is k, so it's equal to k, evaluated at the upper bound, which is h of x, minus k evaluated at the lower bound, which is a. So g of x would be equal to this. It's antiderivative evaluated at the upper bound minus the antiderivative at the lower bound. And then we can find now what g prime is equal to. That's what the conclusion about is on this theorem, what g prime of x is equal to. So let's see if we can find g prime of x. G prime of x, well, the first thing you have here is a composite function. And so follow the rule for the derivative of a composite function. Derivative of k of h of x is going to be the derivative of the outside function, and then substitute in the inside function, and then multiply by the derivative of the inside function, which that looks a lot like the conclusion that we're looking for. And then minus, now k of a, k is some function, and when I plug a constant a into it, I'm going to get some constant out. So k of a is a constant, and of course the derivative of a constant is 0. Just like in our problem that we just worked out there where we had the cosine of 1 at the end, that was just a constant, so its derivative was 0. Now the last part of this, I want to get this in this form that we have above here, where it's f of h of x instead of k prime of h of x. And so you just got to remember our relationship here. If we've said that k of x is equal to the antiderivative of f of x, then by our definition of our antiderivative, our indefinite integral, that means that k prime of x, the derivative of k, is equal to f of x. So k prime of x and f of x are the same function. In fact, that's how we check to see if we have an antiderivative that we think is correct. If we're claiming that k of x is an antiderivative of f, then the way you check your answer is you take the derivative of k and see if you get the function you started out with, f. So we can replace k of x here, or k prime I should say, k prime of x, with f of x. So let's do that here in this last step. So k prime gets replaced with f of h of x times h prime of x, and we'll leave the 0 off, and there we go. There's exactly what we wanted to prove. All right. Let's see if we can use this then. We're going to jump ahead a few examples here. We'll come back and get the other examples as we go. But take a look at example 7 there on page 275. They give us a function defined as a definite integral. F of x is equal to the integral from 2 to 5x of the secant of t dt. Now again, you could go through a process similar to what we saw in that very first example, where we found the antiderivative of that sine function, and then evaluated at the upper and lower bound, took the difference, and then followed that up by finding the derivative. But what we found is this second form of the fundamental theorem of calculus, derivative of an integral form, gives us a shortcut for evaluating this. I don't need to go through and find an antiderivative and then turn around and find the derivative of that. Those two end up undoing each other. And so therefore, f prime of x by the second form of our fundamental theorem of calculus says it's going to be this function, the secant function right here, evaluated at the upper bound. In other words, we take this upper bound and we replace t's, all the t's that you have in there. If you had more than one t, you'd replace all of them with that upper bound. It's the function f evaluated at the upper bound, which we called h of x in our little proof. And then we multiply by the derivative of the upper bound, which is 5. You can see here is a good example where the upper bound is not just x, it's 5x. It's a function of x. And so this turns out to be 5 secant of 5x is the derivative of function f here. Now it turns out with this problem, we have not even covered how to find the antiderivative of secant of t. So you have no other method but to use this to find the solution for what f prime of x is equal to. Unlike our first example where we had the sine function, we knew how to find the antiderivative of sine. Okay, so this works even if I don't know the antiderivative of this function here, I can still find out its derivative. I don't have to go through that process of finding an antiderivative first and then follow it up with the derivative. We can just use this little technique. All right, so that's the definite, or the second form there of the fundamental theorem of calculus. That's the derivative of an integral form. All right, here's a new definition for us. And this is the definition of the ln of x function. And we're going to see that eventually in this chapter that there are some similarities between this function here we're going to define as ln of x and the function that we know pretty well now as the natural log function. But to begin with, we're just going to call this the ln of x function, and then eventually prove in the next section actually that this function is in fact the natural log function that we know. And we'll kind of start to see that relationship show up in this section here. So here's the definition. Well, let's say that ln of x is equal to the definite integral from 1 to x of 1 over t dt. So we're defining it as a definite integral with the upper bound being a variable in terms of some function x. In this case, it's just x. And of course, we're going to say this is true for all values of x greater than 0. We're going to only work with values to the right of the y-axis. And so that's our new function here, ln of x. Now, using the second form of the fundamental theorem of calculus that we just learned, if I have a function that's defined as a definite integral, where the upper bound is some function of x, I can find the derivative of that function using this little technique here. We said that all you have to do is to take this function and you replace your variable in here, which in this case here's my variable. I replace that with my upper bound, and then end up with the derivative of that function. And so turns out that the derivative of this ln of x function turns out to be 1 over x. And this starts to show you the connection to the natural log function that we already know. The fact that this function here has the exact same derivative as our natural log function. We've already talked about the derivative of natural log is 1 over x. This function here, this new function we've defined, has the exact same derivative. Now when that happens, it doesn't mean the two functions are the same. They could still differ by a vertical translation. But it looks they have the same shape everywhere is basically what that means, the same slope everywhere. Thus the two functions have the same shape. All right. Let's take a look at an example now and use this property here. It's actually going to be kind of a review for us because you know the natural log function, but we're going to use this little property really that we know this new ln of x function. So if y is equal to the ln of 7x to the fifth, find dy dx. So we'll say y is equal to the ln of 7x to the fifth. And we want to find out dy dx, the derivative of this. I'll go ahead and write it in that notation. I like doing that from time to time just so you get used to seeing y prime versus dy dx. Those mean the same thing for us. All right, so let's use our property that we just learned here, that the derivative of this ln of x function is equal to 1 over whatever you're taking the ln of, which is 7x to the fifth. That's the derivative of the outside function, and then we substitute it in the inside function. And now we multiply that by the derivative of the inside function. So that's going to be 35x to the fourth. Notice we're following chain rule as we do this. It's a composite function. And now let's just simplify this. 35 over 7 is 5. And x to the fourth over x to the fifth, that's going to be 5 over x. So it turns out this is equal to 5 over x. All right, let's take a look at another derivative function here. It says let y equal cosecant of ln of x. Y is equal to the cosecant of the ln of x. And this time again it says to find dy dx. Again, notice that you've got yourself a composite function, so we're going to follow chain rule again with this. Now the derivative of cosecant, remember your little technique we use to recall these. Derivative of secant, I know is secant tangent, so the derivative of cosecant is a negative cosecant cotangent. So I'm going to go ahead and write that down. Negative cosecant of something times the cotangent of something. And I like using those parentheses when you're following chain rule as placeholders for us. And then the second step of chain rule says you substitute in that inside function. That's the ln of x that we're substituting in. And then finally, chain rule says now you multiply by the derivative of the inside function. The derivative of the ln of x function we just learned is 1 over x. Again, when we're talking about ln of x here, we're talking about that new definition we just saw where it's the definite integral from 1 to x of 1 over, 1 over t dt. All right? And so this turns out to be equal to, I'll put the 1 over x, I guess, out front here. So it's a negative 1 over x cosecant of the ln of x cotangent of the ln of x. There is our derivative. All right, let's try one more of these. This one says if f of x is equal to, this time it's a product, x cubed times the natural log, times the ln of x. I'm going to try to not say the natural log here as we go through this. Times the ln of x, because we haven't quite proven that this is the same as that natural log function. We will. And it says find an equation for f prime. Okay, so let's find f prime of x. And so we're following product rule here for this. So derivative of the first function, derivative of x cubed is 3x squared times the second function, ln of x, plus the first function, x cubed, times the derivative of ln of x, which again, we've learned in this section based on our definition of ln of x, its derivative is 1 over x. And we can simplify that here a little bit as 3x squared times the ln of x plus x cubed over x would give us just x squared. All right, in fact, if you wanted to go one step further, you could factor out an x squared. You don't need to do that, but I'll just show you what that looks like. If you do factor that out, you end up with 3 ln of x is the factor left in the first term, plus just 1 when I factor out or divide out that x squared in the second term. So there we go. Now it also said, then show graphically and numerically that your answer is correct. So let's just check that real quick here. If you, let me switch over to the calculator so you can see that. So if we take our calculator, and we'll check, first of all, that we end up with graphically the correct solution here. So I'm going to put into y1 here, our original function, which is x cubed times the ln of x. And in y2, let's sketch the derivative function that we came up with, which our derivative was equal to 3x squared ln of x plus x squared is how we simplified that. I guess you could also put it in that factored form if you wanted to write it that way as well. That's what we came up with. And then let's sketch the numerical derivative. Recall how to do this on your calculator. You can go under your math menu and grab the nderiv command. And in our case, we're going to tell it to take nderiv of y1. And our variable is x, and our value is x. In fact, I'm going to shut off y1 because we don't really need to have that graph along with it. And in fact, I'm going to change this sketch here. So it puts this little circle so we can actually see it sketching right on top of the derivative function here. Hopefully we will see that. And let's set up our window here. I'm going to go from let's make a small window here from 0 to 2 for our x's and 0 to 2 for our y's. And we'll just graph that. Actually, I need to see a part of the negative domain here, or negative range here. Let me change that. Let's go from -2 to 2 for our y's. It starts out below the x-axis, just so you can see that. If you want to see more of this graph, you certainly can change your window there, but there we go. We can see graphically that we're getting the exact same thing. It traces that curve out. And then to check this numerically, we can just flip over to our table and set up our table so that it can go through some x values and just show us that we get the same value on each function. So let's do that. Let's go to our table. Let's start it out at 0.5, since this involves the ln of x function, which is only defined for positive domain. And let's set this at a half here. Should be decent. You could set it smaller if you want to see more values closer together, but here we go. You can see the values for y2, which is our derivative, compared to the values of y3, which is the numerical derivative. And you can go through those values and just check to see that you keep getting the same value over and over again. That's a pretty good sign that you've got the correct derivative, obviously. All right. All right, and that's the end of this first part of this section.